Welcome to the second lecture on beta binomial model. In a Bayesian setup, main objective is that we want to model two parts of a problem. In a Bayesian perspective, there are known part and there are unknown part. Some quantities will be known to us and some quantities will be unknown to us. The known quantity is the data, typically denoted as D. The unknown quantities are the parameters, typically mean, variance, it could be missing data, or the variable we want to predict. We denote them with theta. To make inference about unknown quantities, we split a joint probability function that describes how we believe these quantities behave in conjunction, joint probability of theta and data. Using Bayes' rule, the joint probability function can be rearranged and make inference about the theta. We can come up with a conditional probability of theta given D as probability of D given theta into P of theta divided by P of D. Now P of D given theta is effectively the likelihood function of theta, which typically we write as L of theta given D times P of theta. And P of D is written as integration over theta, L theta given D times P theta D theta. So typical Bayes theorem is being applied. Now L theta given D is the likelihood function of theta. P of D, which is the denominator here, integration L theta given D times P of theta D theta is the normalizing constant of prior predictive distribution. It is normalizing constant because it ensures that the posterior distribution of theta, this is the posterior distribution of theta, integrates to 1. So if you integrate posterior distribution of theta over theta, then it will be 1. And that is being ensured by this normalizing constant P of D, and this act as a normalizing constant. It is the prior predictive distribution because it is not conditional on previous observation of data generating process or the prior, and it is the distribution of an observable quantity or typically called predictive. Popular presentation of posterior distribution is often presented as probability of theta given D is proportional to L of theta given D times P of theta. Posterior is proportional to likelihood times prior. Since the denominator is behave as a normalizing constant, we can write it as posterior distribution as proportional to likelihood times prior. Why are we allowed to do this? Because this is a normalizing constant in the below, and because it's a normalized, the denominator behaves as a normalizing constant, so that's why we are allowed to do this. Why might not be as useful? Because if you see, this part, all we have is the right hand side, and just multiplying likelihood times prior will not actually will give us the probability or the posterior probability. So we cannot directly use just the functional form of the likelihood and prior and make use of it. So we have to do slightly more, we have to handle it little bit more carefully to get the final solution. Now we will introduce the Bayesian analysis for binomial distribution. Suppose x1, x2, xn are independent random draws from the same Bernoulli distribution with parameter pi unknown. Now pi is the unknown parameter is typically proportion. So don't please mix up. Pi is not the universal constant pi. Here I am using the Greek letter pi as to make the value proportion to mean it is proportion. The value of pi here is 0 to between 0 and 1. Pi stands for proportion here. So xi follow Bernoulli distribution pi. These all xi's are independent. So we can write sum of all xi's y equal to summation xi. These follow binomial distribution n comma pi. N is the number of sample size and pi lies between 0 and 1. The joint distribution of y, so y is my data, y is my observed data. You can call, we know that it is y is a sufficient statistics for x1, x2, xn, and pi is the unknown quantity. So the is the product of the conditional distribution of y and the prior distribution of pi. What distribution might be a reasonable choice for prior distribution of pi and why? These questions we will come back to again and again, because choice of prior distribution is going to affect our result quite significantly. So we always have to choose our prior distribution for unknown quantity very carefully. If y follow binomial distribution with parameter n and pi, n is known to us and pi is not unknown, pi is between 0 and 1, a reasonable prior distribution for pi must be something bounded between 0 and 1. One option is uniform 0 1, uniform distribution between 0 and 1, and that is actually very popular prior, because in uniform 0 1 is just a flat prior, and whether pi value is 0.3 or 0.5 or 0.6, I have no prior fascination. I do not have any likings or dislikings for a particular value of pi over the another value of pi. I do not have any liking for 0.3 with respect to 0.6. All the values on the pi between 0 and 1 has the same prior probability. Posterior distribution, that p of pi given y, can be written as the likelihood times prior. So likelihood is ncy pi to the power y 1 minus pi to the power n minus y times the prior distribution. Now prior of pi is just 1 between 0 and 1, 0 otherwise. As it happens, this posterior distribution turns out to be proper posterior distribution. What it mean by proper posterior distribution? Turns out this function, you can have a proper normalizing constant, and the final resulting posterior distribution turns out to be a proper probability distribution. That means if you integrate out to the pi, you will get exactly 1. So that's why it's called proper posterior density function. Question is, how can you say so? Let us try to solve this problem. Y suppose follow binomial n pi and pi follow uniform 0 1. The posterior, the up to proportion can be written as pi to the power y 1 minus pi to the power n minus y. In choose y, this will behave as a constant, so it is not going to affect much except the normalizing constant. So we can simply write it in this way. You cannot just call posterior a binomial distribution, because you are conditioning on y and pi. Now here pi is random variable, so you have to be careful. Y is completely known to you, y has the exact value, y behave as a constant. So in this form, y and these are known quantity to you, these are data, and this behaves as a constant. What is not known to you, the unknown quantity pi, behaves as a random variable here. So you cannot say that this is actually a binomial distribution. However, there is another distribution which has a similar structural form, and that is called beta distribution. Now if you look in, this is the PDF of the beta distribution, beta with two parameter alpha and beta. Beta distribution, if you just look into this, so x follow beta distribution between 0 x follow between, I mean have takes value between 0 and 1, x to the power alpha minus 1 and 1 minus x to the power beta minus 1. Now you compare this form with this form. So we can say that this posterior distribution, or the kernel of the posterior distribution, behaves somewhat like beta distribution. And we are going to use this structural similarity in our favor. So if we choose here x equal to pi and alpha equal to y plus 1 and beta equal to n minus y plus 1 and plug it in here, then what we get is the posterior distribution of pi given y actually follow a beta distribution with parameter y plus 1 and n minus y plus 1. So this is an interesting news for us. So what it says that posterior distribution of pi, which is unknown quantity, whose posterior distribution is completely known to us. Posterior distribution completely known to us because it has, which follow beta, we know exact form of the beta, and it has two parameter a and b, and these two parameters have exactly y plus 1 and n minus y plus 1, and we know the exact values of y and n because this is just a data for me, and this is the exact PDF form of that. And gamma n plus 2 and gamma y plus 1 gamma n minus y plus 1, this will behave as a normalizing constant to transform this pi to the power y and 1 minus pi to the power n minus y into proper posterior distribution, a proper probability distribution. A researcher examined the level of consensus denoted by as pi among n equal to 24 Guatemalan women about whether or not polio, as well as some other disease, was thought to be contagious. In this case, 17 women said polio was contagious. So we can define our problem x sub I equal to 1 if respondent I thought polio was contagious and xi equal to 0 otherwise. So sum over I equal to 1 to 24 xi equal to y. So the y is the number of women who thought the polio was contagious, and here in this case we have y equal to exact value 17, follow binomial distribution 24 pi, and we assume say pi follow uniform 0 1, which turns out to be also a beta distribution with parameter 1 1. We can say this pi distribution, now the whether it is contagious or not, this pi has a probability distribution, a posterior probability distribution, which is beta y plus 1 n minus y plus 1. Now plug these values n equal to 24 and y equal to 17, then we have a posterior distribution of awareness, if pi you call it consensus or the awareness among the women about the or the sub of the population whether polio or other disease are contagious or not, that has a posterior distribution beta 18 comma 8, and beta 18 comma 8 has a nice beta distribution, sort of a bell shape with around zero point 0.7, near 0 point 0.7 has the highest probability, and with the behavior somewhere between, you know, in maybe 50% to 90% confidence, most of the probability mass between 50% to 90%. The full posterior contains too much information, because if you just see this, if I just tell this kind of thing, that it is too much information for us simple people or a policy makers to make anything out of it. Especially it is a one parameter model, still we can probably make something out of it, but if it is a multi parameter model, then it is too much. So what we do, we use summary statistics of the posterior distribution, like we look into mean, variance, highest density region and stuff like that. So the method for generating summary statistics there are two methods. One is the analytical solution. We use well-known analytical solution for the mean, variance, etc. of the various posterior distribution. Another is you use a numerical solution. What you can do, you can simulate random samples from the posterior distributions and take the average of those, or the calculate the statistics, summary statistics of those random numbers. So this is typically the two methods we can look for. Analytical summaries are based on standard results from probability theory. Now let's continue in our example. So our posterior distribution of pi, given the data, it follows beta distribution with parameter 18, 8. We know if theta is a random variable which follow beta distribution alpha comma beta, then you can pick up any textbook and probably you will get these results that expected value of theta will be alpha over alpha plus beta. Variance of theta will be alpha beta by alpha plus beta whole square times alpha plus beta plus 1, and this will be the mode. So all the mean, variance, mode of beta distribution is well known to us, and it is available in most of the textbook, or if you just google it in the internet, you will get these results. All now we have to do, we have to plug these values into these 18 alpha and beta and then 18 and 8 in these formulas, and that gives us the result. So expected value of pi given data is 18 over 18 plus 8, which is 0.69. Variance of pi is 0.01 and mode is 0.71. So we can say that posterior estimates of the, or the Bayesian estimates of pi is zero point 0.7, near 0.7, we can say that, whereas the frequentist estimates or the likelihood estimate will be 17 by 24, which is also near 0.7. Now what we can do, we can simulate thousands of samples from beta distribution 8, 8 and compute the mean, median, minimums, maximum, standard deviation and everything, and that turns out to be 0.69, 0.68. Median is 0.69 and mean is 0.68. So that is the numerical solution. So this is the analytical solution. But remember that in the analytical solution, this expected value is being found out by solving an integration, right? Now this integration, you need, if in this beta, for the beta distribution, we know the solution of the how to solve this integration to get the expectation or variance. But if we don't know what is the actual analytical solution for mean or variance, then what you can do, you can simulate the thousands of samples from the posterior distributions and take the average of those samples. Now I will talk about another interesting concept called highest density region. Highest density regions or highest density interval contain a specified probability or posterior probability. The figures below tells us a 95% highest posterior density region. So it's equivalent to a confidence interval. If I can come up with a two values between which 95% of the most of the probability lies in, then we can say that with 95% probability we know the true value of pi lies in this region. So this is a Bayesian interpretation of what we typically call confidence interval in standard textbook classical statistics. Bayesian credible interval is the probability that a true value theta lies in an interval. Technically, probability that theta belongs to an interval given the data is alpha. Note that here probability statement is very direct. That is absolutely direct statement. There is no, goofing around here and there. Whereas in the frequentist confidence interval, it says that frequentist confidence interval is the region of sampling distribution of theta such that given observed data, one would expect about 1 minus alpha percent of the future estimates of theta to be outside that interval. Note that here understanding of probability is implicit. It is not a direct probability statement. Whereas in the Bayesian credible interval, it is a direct probability statement. It says probability, the true value belongs to this given the data is alpha. The interpretation is very direct, very straightforward. Whereas in the standard classical confidence interval interpretation, the probabilistic understanding is implicit, indirect statement. Though Bayesian credible interval and the frequentist confidence interval are different in their interpretation, oftentimes they turns out to be similar. The result turns out to be similar. So you don't confuse that, okay, I should expect a very different result. Turns out to be they may have a very similar result. Bayesian results and the confidence interval standard frequentist classical results may give you a very similar results. The main difference often turns out to be the interpretation. If Bayesian use a non-informative prior and there is a large number of observations, often several dozen will do, HDRs and a frequentist confidence interval will coincide numerically. So you may get from a Bayesian interval and a frequentist interval, they will coincide with each other at least numerically. But the difference will be the interpretation. Whereas the Bayesian confidence interval or the Bayesian credible interval will give you a very direct interpretation of a probabilistic statement, whereas in frequentist method, the interpretation of confidence interval is very implicit, not a direct statement. So that is a major difference between the Bayesian credible interval and frequentist credible interval. If we let's return back to the binomial distribution example. If y follow binomial n by the uniform prior is just one of the infinitely many number of possible prior distribution, what other distribution could we use? A reasonable alternative to the uniform 0 1 distribution is beta distribution itself, because beta distribution also has a support between 0 and 1 only. So can you show that beta 1 1 is a uniform 0 1 distribution? I'm leaving it you for assignment. I'm not going to work it out here. Here I am showing that if you choose beta 5 5, how your prior distribution will look like. If you choose beta 3 comma 10, then how will your prior will choose like. If you choose say beta 10 comma 3 or beta 100 comma 30, then how your prior will choose like. Now you can imagine these are only 4 ad hoc choices that I had made, but you can make infinitely many choices of these prior parameters, and that will lead to the infinitely many prior distributions. Immediately one criticism will be, look, you have infinitely many choices of prior, so that means you have effectively infinitely many choices of posterior distribution. Does that mean that Bayesian solutions are not unique in that sense? Yes, if you take that literally, it means there could be literally lot of different choices will lead to lot of different solutions. But how Bayesian statistics handle this issue, I will come to that little later, but I will interestingly use I give you an example that how modeling experts' opinion with beta prior can help us in this way, in this particular problem. Suppose a subject matter expert believes the chance that a value of pi is less than zero point 0.5 is less than 0.05. That means in that, with respect to the application that we are discussing, with respect to that, a subject matter expert or there are historical evidence, there may be a published paper which indicates that the probability of pi is less than half, less than median, is very slim, and we maybe it is less than 5%. In addition, the prior expert also believes that the sub that the chance that the value is more than 90% is also very less. That is also that pi is greater than zero point 0.9 is between 0.05. So if we combine these two, then effectively expert believes that the true value of pi is between zero point 0.5 and zero point 0.9, and that probability is greater than zero point 0.9. Now, what we did, I used this information and figured out that there is a beta distribution 9.2 and 4.3, comma 4.3. These beta distribution actually satisfy this equality, this this condition with equality. Okay, so we can choose, we can say this beta 9.2 and 4.3 is a probability distribution which actually models the expert's opinion about pi. Now I have modeled the expert's opinion about pi. I can use this beta distribution as the prior, because expert's opinion is also an information, and I want to use, if I want to use that information in my study, there should be a way, and Bayesian way is one way of doing it. So if you can, I have used this information to develop a distribution, here in this case beta distribution 9.2 comma 4.3, and use which I believe this beta 9.2 4.3 actually models the expert's opinion about pi, and I'm going to use that as my prior distribution. And if I have this beta, now what happens if y follow binomial in pi, my pi follow a beta distribution with some alpha and beta. So the posterior distribution turns out to be the likelihood ncy pi to the power by 1 minus pi to the power n minus y. This is the PDF of beta distribution divided by the denominator p of y. Now what is p of y? P of y is integration 0 to 1 ncy times p to the power y 1 minus p to the power n minus y times this uh, prior distribution times t of pi. If you solve this, this is a very complicated integral in the denominator. Though this particular integral can be solved, but we will pretend that it is difficult integral, and we shall use a standard trick in the Bayesian toolbox to solve this problem. The posterior distribution turns out to be this. Okay, this is my posterior distribution turns out to be. If you simplify the above expression, then it turns out my posterior distribution is a beta y plus alpha n minus y plus beta. I am leaving that as an assignment to figure out what is f of pi. F of pi, all you have to do, solve this integration. If you solve this integration and plug it in here, and you do the cancellation and all the thing, then you will find that posterior distribution of beta turns out to be pi turns out to be beta with y plus alpha comma n minus y plus beta distribution. You can see the posterior distribution has the same distribution as prior. So we started with prior distribution, which is beta distribution. This is my prior distribution. We started with the prior distribution, which is a beta distribution. My posterior turns out to be beta distribution. Again, it belongs to the same family of distribution. Of course, my parameters are now updated. Parameters are being updated given as we have seen the observed data. But my prior distribution and posterior distribution belongs to the same family. Since they belongs to the same family, and I know most of the analytical properties of the prior this beta distribution, that helps me to develop all the analytical solution about the posterior distribution. So as you can see, the prior posterior distribution has the same distribution as prior distribution updated by new data. In general, when this happens, we call this such a prior as conjugate prior. Now let us go back to the application. Let's continue to the previous example. So you remember we have 17 out of 24 women say polio is contagious. So y is 17, n equal to 24 is the sample size, where y is the realization of a binomial. So we use beta 9.2, 4.3 as our prior. The posterior distribution now 17 plus 9.2 comma 24 minus 17 plus 4.3. So I'm just plugging the value of y, alpha, n, y and beta in this, and turns out my posterior distribution is now beta distribution with 26.2 and 11.3. So this blue color distribution is my prior distribution, and the red color is the posterior distribution. And on the x-axis I have pi, y-axis I have the density, the posterior prior density and posterior density. I have plotted the likelihood on the same thing with the green color, and this is the effective prior distribution, beta with 9.2 and 4.3, and posterior is the red with parameter 26.2 and 11.3, and the likelihood is the green one. If I would have choose beta 10.3, posterior turns out to be 27.10. So this is the, you can see this is the slight change, actually changes the prior behave little behavior. Actually 10.3 is stronger prior than actually what we have here in the experts prior. So this is a stronger prior because it is much more shift towards the right, and as prior shifted, the posterior also shifted little bit towards the right side. Now we have considered a prior 3,10, which is a really bad prior. The posterior has tried to correct itself by taking a distribution somewhere between likelihood and the prior, but it's still quite far from the data. Now we took a prior which is 30, 100, which is not only far from the actual data, which is also very confident, not only bias or wrong, which is also very confident, and still posterior is trying to go away from this prior, but it's now this time because the variance is very hard, I mean small, the strong confidence interval is very small. At this time it is not able to move far from the prior. So now we will conclude the today's lecture. Conjugate prior can be used to model experts' opinion, and that is one of the advantage of using conjugates prior. People do criticize conjugate prior by saying that, oh, it is too mathematical form, and it is a real form might be quite different. True, but it is also useful to model the expert's opinion. For conjugate prior, we don't have to solve complicated integration. That is an advantage of conjugate prior. Analytical solution for conjugate prior is known. Now it is time for hands-on. In the next lecture, we will do hands-on.